my name is Reagan Wakefield, and this is my Physics 2211 Constant Velocity Lab. To begin, I'm going to outline the purpose of this lab and explain some relevant physics principles. The purpose of this lab is to observe the motion of a moving object that is moving at a constant speed and is not changing direction. We will do this by observing the motion of a physical object and comparing those results to a computational model based on physics principles. The first fundamental physics principle is Newton's first law, which states that an object in motion will stay in motion and an object at rest will stay at rest, unless acted upon by an external force. The second principle is Newton's second law, which states that an object's acceleration depends on the force acting upon an object and the object's mass. Finally, constant velocity is when an object moves in a straight line and has a consistent speed. Constant velocity occurs when the net force equals zero. In other words, when all the forces acting on the system cancel out. In this lab, we will be investigating an object with constant velocity. For the experimental method, we will be moving a physical object and investigating its motion through an online tool called Tracker. The system is the moving object, in this case, an object on a slider, and the surroundings are everything else around the system, such as push force, gravity, and friction. For the computational method, we will be using GlowScript. We will use two important formulas called the position update formula and the velocity update formula. Both of these formulas are derived from Newton's second law. These formulas allow us to predict the final position and velocity of an object based on initial conditions. The position update formula states that final position equals initial position plus average velocity times the change in time. The velocity update formula states that final velocity equals initial velocity plus net force divided by mass times the change in time. In addition, we will also use the average velocity formula to determine the initial velocity of the object. I used this video and tracker to track the motion of the object by plotting its position as a function of time. As you can see, the object is moving from right to left. I chose my axis so that the right side is positive and the left side is negative. This results in a downward sloping graph of position versus time, which can be seen on the right side of the video. Something important to note is that I started the time at t equals 0.7 seconds because that was when we let the slider go and it began moving in a constant velocity. So instead of t equals 0, my initial time was t equals 0.7. Moving on to the computational method, here is an excerpt of my code that outlines the initial conditions. I left the object's mass as the default value of 1 because the mass of the object is not important for our calculations in this lab. I set the initial position to 0, 0, 0 and set the initial velocity to negative 0.6700. I obtained the initial velocity by calculating the average velocity between the first 7 frames from Tracker. As I mentioned before, I set my time to begin at 0.7, and I also set my delta t to be 0.033. I obtained this by dividing the total time of the video by the number of frames. This next excerpt of code illustrates the physics principles we discussed in the introduction. I set my net to be 0, 0, 0 because the object is moving at a constant velocity and thus has a net force of 0. I also incorporated the velocity update formula and position update formula that I mentioned earlier. Here is a graph of the data points from both the computational data and the experimental data. The x-axis is time in seconds and the y-axis is position. As you can see, the data is very similar at the beginning, but as t increases, the data begins to diverge. The predictive model remains linear, while the observed model has a bit more inconsistency. The fact that the computational data is linear showcases that the object maintained its constant velocity, whereas in the observational data, the velocity does not remain constant. This could mean that the net force is no longer 0 due to forces like friction. Now we'll discuss some follow-up questions. The first question is what would happen if we flip the x and y axes in Tracker? In my experiment, I chose the right side to be positive and the left side to be negative, and this resulted in a downward sloping graph. If I flip the axes, the graph would change to sloping upwards. The results, however, would not change. I would draw the same conclusion from an upward sloping graph as I would a downward sloping graph. The next question is, your observations can be predicted well by your computational model when you set net force equal to 0. Is it possible to say how many pushes and pulls are added together to give 0 net force? The answer to this is that no, you can't really say how many pushes and pulls are needed to give a 0 net force. In our real world experiment, it's very difficult to obtain a constant velocity because humans aren't perfect. By pushing the object, we can cause it to accelerate, and forces like friction can cause the object to decelerate. Therefore, we are unable to get a perfect constant velocity like in the computational model. Finally, some source of error I had was that when we pushed the object, we may have pushed too hard, resulting in an inconsistent velocity. And this was also my first time using Tracker and GlowScript, so I could have some small errors through the use of these technologies. Thank you for watching. I hope you enjoyed.